ஆண்டனி சார். ஓ! ஆண்டனியும் லாக் பண்ணியிருக்காரு. என்னது?
ஜேக்கப் சார்.
சார் கேக்குதா?
கேக்குது சார்.
ஓகே சார்.
இந்த பார்ட்டிசிபென்ட்ஸ் எல்லாருக்கும் வெல்கம் மெசேஜ் ஒன்று சாட்ல போட்டு விடுங்க.
நான் தான் வாங்கிட்டு இந்த கையில போடக்கூடாது கல்ல தண்ணி அப்புறம் குடிக்கிறதா இல்லையா சொல்லிருக்க அவனே வரல
ஸ்லிப் கிடைக்கிறாரு இப்பதான் நம்பால அவரு ஸ்லிப்ல தானே இருக்கு.
சண்முகம் சார், ஹலோ சண்முகம் சார்.
ஹலோ ஆண்டனி சார். ஆண்டனி சார், இப்போ ஃபாதர் 3 பேரும் நீ அன்மில் பண்ணிட்டீங்களா? ஓகே பண்ணிட்டீங்களா? அன்மியூட் பண்ணிட்டீங்களா?
இது ஜூம்ல 100 வருவாங்க.
ஓகே ஓகே ரெடியா இருக்கு.
யூடியூப் லைவ்ல மேக்ஸிமம் 300 பக்கத்துல ரெஜிஸ்டர் பண்ணது கிட்டத்தட்ட 400 பக்கத்துல ரெஜிஸ்டர் பண்ணிருக்காங்க. 400 இதுவா? இதுவா இல்ல சார். ப்ரோக்ராம்
பேசுறது
சார்
வீடியோ
ரெடியா இருக்கீங்களா?
இமேஜ்
வச்சுக்கிற மொபைல் ஆன் பண்ண சொல்லுவா, ஆஃப் பண்ண சொல்லுவா. சரி சரி.
ஆனா உள்ள வரவே இல்லை. கிளிக் பண்ணி
என்னது? சூப்பர்.
ஓகே தானே?
இந்த இப்போ வந்துடும் 2 மினிட்ஸ் தான். 2 மினிட்ஸ் தான். சரி.
Wilson sir.
Yes.
Sir, that professor name Vanga Ganesh.
Oh, okay.
Just note it.
Vanga Ganesh.
Yes.
அவர்தான் நமக்கு அரேஞ்ச் பண்ணி கொடுத்தாரா?
Same university. Yes sir.
Okay. அவர் என்ன ஃபீல்ட் ஆஃப் ஸ்பெஷலிஸ்ட் அவரே சொல்லிடுறேன்.
அவர் இதான் சார் மெட்டீரியல் சயின்ஸ் தான்.
எல்லாத்தையும் ஆஃபீஸ் நீங்க முடிச்சிட்டீங்களா? ப்ராஜெக்ட்ஸ்ல செக் பண்ணிட்டீங்களா? ஆடியோ இருக்குதா? ரெக்கார்ட் செக் பண்ணிட்டீங்களா? இல்ல ஆடியோ இருக்கு இல்லையா? ஷேர் பண்ணலாம். எங்க இருக்கு? ஷேர் பண்ணிக்கலாம். வீடியோ எங்க போச்சு? எங்க இருக்கு? சரி சார், நான் பேசுறேன். எனக்கு கிடைக்க முடியா? பேசுற கேக்குது. சொல்லிட்டு
Good morning to all. I feel immense pleasure to welcome you all for the international webinar on the progress in nanocomposites for environmental and device applications. Now I invite Dr. K.S. Joseph Wilson, Head Department of Physics, to deliver welcome address.
Good morning, everyone.
Meeting.
First of all, I have immense pleasure to welcome Reverend Father John Pragasam, the rector, Reverend Father Gilbert Camillus, the secretary, and Reverend Father Godwin Rufus, the principal of our college. Our hearty welcome to you, fathers. Professor I.S. Yagia is a renowned scientist in the field of optoelectronics and nanotechnology. In spite of his very busy schedule, he has given his consent to present his invited talk in this webinar. So on behalf of the management and the Department of Physics and the participants, I wholeheartedly welcome you, sir. Also, I welcome Dr. Vanga Ganesh from the same university. I welcome you, sir. Here, there are a number of participants all over the world. On behalf of the PG and Research Department of Physics, a very warm welcome to you all. Have a nice day.
Thank you, sir. Next, I would like to invite Reverend Dr. John Prakasam, SJ Rector, Orlanandar College, to give felicitations.
Good morning to all of you. I'm really happy to participate in this webinar on a very interesting topic to both chemists, physics, and all those who work in interdisciplinary areas, because it involves the current topic, nanocomposites, which is an area bordering all physical sciences, and particularly for those who are not familiar with the idea of composites, it's as old as our forefathers who started using jewelries. After all, pure gold cannot be used for any jewel making purposes. It's very costly, but not that much useful for people. If you add a little bit of impurity, like some alloys, silver, copper, and so on, it makes 22 karat gold, which is very much used by all the people. So sometimes what we call impurity can be very, very useful to make the materials quality-wise better, physical properties improved, and so on. So I am talking in an ordinary language for a layperson. Idea is continued in nano materials today. Only the difference is that we add in very small quantity. The dimension is very, very small. Controlling this impurity makes the material behave differently, particularly at the bordering, what you call the interfacial interactions is very much involved in this form of material that makes it very useful for us today, particularly when you are dealing with electrical properties of materials. Certainly, so much research is done today in this area, and all the more it makes it more interesting when someone working outside India is the resource person today, Dr. I.S. Yagia. I appreciate his willingness and to participate and enlighten us on this topic today, in spite of the many hardships that we are all facing. Academically, we are all united. That gives us a lot of enthusiasm, particularly for the research scholars to continue their work. And I wish this webinar all the best, particularly the department head, Dr. Wilson, and professors, Dr. Shanmugaraju and Dr. Valanarasu, those who are organizing this webinar today. I wish all the best for the success of this webinar. Thank you.
Thank you, Father. Now I invite Reverend Dr. Gilbert Camillus, SJ, Secretary, Orlanandar College, to give felicitations.
Good morning, fathers and professors.
I'm really delighted to be here with you for this wonderful webinar organized by the Department of Physics, Arulanandar College, Autonomous, Dharmatur. It's a wonderful program the department has envisaged, and it has come into reality today, and we are here attending this webinar. The topic, the progress in nanocomposites for environmental and device applications, is a very useful topic. It will be useful for the students very much, I suppose. So first of all, I would like to congratulate the department, the department HOD, the head of the department, Dr. Joseph Wilson, and also his colleagues for having organized this useful program, not only for the students, but also for all the scholars. We all know that science is supposed to be used for creative purposes. And we are all called to become co-creators in the act of God's creation and in protecting nature. And this topic is going to be very useful for the students, how to handle nature by applying this science nano techniques in their day-to-day field scientific arena. So it's going to be a really useful exercise for the students when they attend this program. This nanotechnology is not only a very current one, maybe I think I have been hearing about it for the last 10 years. So this is now here applied, and we have got a very efficient resource person from Saudi Arabia, the university, King Khalid University. It's a wonderful place, Saudi Arabia, a peaceful city, peaceful place. And we are really fortunate to have this Professor Dr. Yahya Ibrahim. I wholeheartedly welcome him on behalf of our institution and on behalf of the department. It's when I think of this nanotechnology, it's a branch of science and technology which deals with the manipulation of individual atoms and molecules. A nanometer is 1 billionth of a meter. It has a wide application in all the fields of science and technology. So now nanotechnology has the potential to affect environmental protection through understanding and controlling of emissions from a wide range of sources. So it can protect nature. It will be useful in that process. It minimizes the protection of the undesirable byproducts and remediation of existing wastes. The application of this field ranges from computer to medicine. Medicine also, they are applying this. For example, tissue engineering and cellular therapies, they are applying this technique. Now, nanocomposites techniques are used in biomedical area also. So this application, through this new materials and devices, we are having new products by using this application. So I wish you all the best in delivering, having this deliberation, and this will be useful for the students in their day-to-day studies when they are applying this technology in their Department of Physics. Once again, I congratulate everybody who was involved in this wonderful intellectual deliberations. Thank you. Wish you all the best.
Thank you, Father. Now I'm happy to invite Reverend Father Godwin Rufus S.J., Principal, Arulanandar College, to give presidential address.
Learned professors, beloved students, future scientists and research scholars and lovers of science, I wish you all a very good morning. It fills me with joy as I sit before you all, viewing at this little computer to see you all in little cabins, one of the new innovations of COVID-19. I'm happy, dear friends of science, that you have spared at least an hour for some intellectual brushing up, keeping aside all your entertainments and fun-filling works and delicious kitchen skills for a while. In the 3rd century before the birth of Christ, Archimedes, perhaps the very first known physicist, appeared before the public in a marketplace, and in a voice sounding like a thunder, he said, "Give me a lever long enough and a fulcrum on which to place it, and I shall move the world." He said, "Give me an opportunity and I shall move the world." All thought that he was a madman and laughed and giggled at him, and they continued with their own business. Only a very few again, went to him and asked, "Are you serious, old man? What is your basis upon which you say this? Because you are not a madman as the world thinks." And looking into the eyes of his would-be students who would revolutionize the world later, he said, "The effort, that is force, moves over a large distance to move the load a smaller distance, and the fulcrum is between the effort and the load." Yes, they took the point, and the bright students and the listeners asked him again, "Sir, could we move the world?" And Archimedes this time did not answer. He did not answer them, but wisely smiled at them and got into his world of science and philosophy. But his students, who took him serious, went on carrying his wisdom with commitment and determination, and they invented the piler, the cutting plier, scissors, the crowbar, a claw hammer, seesaw, weighing balance, without which no engineer would have built the skyscraper of the digital world, the world banking and financing, multi-specialist hospitals, and even playground. It all started with a new idea which blossomed in a meeting, nay, a conference. The world is afraid of new ideas because they have to change themselves. Accepting a new idea means to give away or sacrifice what they had it and treasured it for a very long time. So they cheat themselves and act as if they are comfortable with old ideas. Galileo was not accepted with his theory of Earth revolving around the sun. The Wright brothers were thought by his own relatives and even his father that the brothers were insane people who have got out from the mental asylum when they said, "Now we can fly in the air like birds." Who are you, my friends? Where are you, my friends? And with whom are you, my scholars? To be normal is very easy. Just follow the norms. You and I can be normal persons like a cog in a machine, or like a person in a market, or among the gathered crowd. But it needs courage to answer a call, my dear friends. It needs courage to be different and even to think differently. We need an opportunity to be different, and Arulanandar College Karmatur is giving you an opportunity. The members of the Society of Jesus, usually known as the Jesuits, are known for many innovations and very specially in the field of education. Along with Loyola College Chennai, St. Joseph's College Trichy, and St. Xavier's College Palayamkottai, the Jesuits not only run schools and colleges, but also shine in fields of social work and communication. Arulanandar College Karmatur is set in a rural setup, providing the rural students with urban facilities. Today, many girls and rural boys have become scholars and they have got a job. It is because of Arulanandar College Karmatur. The research department of physics is a star department of Arulanandar College Karmatur. It has produced not just wonderful and bright students, but has given birth to research scholars and scientists who are praised around the globe. I feel elated that once again the Department of Physics, under the leadership of Dr. K.S. Joseph Wilson, is organizing an international seminar. I'm sorry, the new coinage, the international webinar on the progress in nanocomposites for environmental and device application. I'm sure the scholars will agree that nanotechnology is the talk of many scientists. I'm sure there are many avenues in future towards greater inventions and knowledge innovations in this field. I'm confident that this seminar will give the intellectual audience a lever, that of Archimedes, to move and change the world for the good of the poor and the needy. I heartily appreciate the efforts taken by the Department of Physics of our Lawnandar College to organize this webinar. I also earnestly request the department to organize many more such seminars and webinars and share the knowledge with those who are earnestly in need of such intellectual pursuit. Let all that we do be for the greater glory of God and his people. Have a fantastic and bright afternoon. Wish you all the very best, and God bless you all. Thank you.
Thank you, Father. Next, I invite Dr. S. Valanarasu to introduce the resource person.
I am very happy to introduce our speaker, Dr. I.S. Yagia, Head of Nanoscience Laboratory for Environmental and Biomedical Applications, Semiconductor Lab, Department of Physics, Ain Shams University, Egypt. Currently, he is working as an Associate Professor, Department of Physics, Faculty of Science, King Khalid University, Saudi Arabia. He received his PhD degree in Semiconductor Metal Oxides in 2007 from Ain Shams University, Egypt. In 2012, he was promoted to be an Associate Professor of Semiconductor Materials and Devices. He worked at the Semiconductor Laboratory in Department of Physics, Faculty of Education, Ain Shams University for more than 22 years as a lecturer and associate professor. His research interest includes semiconductor materials and devices, nano metal oxide thin films, powders, organic materials, polymer materials, nanocomposite, and bioceramics. He won 3 prizes. First one was State Incentive Award in Physics from the Academy of Science and Technology, Egypt, 2012. Second was the award of Abdul Hamid Shoman for Young Arab Researchers in Physics in 2013. In March 2017, he won the King Khalid University Distinguished Prize for Teaching. He published more than 360 international papers with a H index of 36, with total citations of 4,656, with the RG score of 45.89. Such an eminent professor with us, I request Professor Yagia to continue your session. Thank you.
Dear participants, please post your questions in the chat box. Your doubts will be clarified at the end of the session. Over to Professor I.S. Yagia.
Thank you. So I needed to, please, you can close your PowerPoint.
Okay, okay,
Good morning for our friends and students and colleagues. I am happy to join the webinar between us here from King Khalid University and the College of Anandar with our friends. So special thanks for the kind invitation, and really I am happy to join all. Thank you for the introduction, and thanks for our friends join here, the rector, secretary, head of the department, our friend Valenzo, and also my friend here in King Khalid, Dr. Ganesh Fanga, to arrange this webinar. Really, I am happy to join us. So let's start by our presentation today about progress in nanocomposite for environmental and device applications. This is the relation between India and Egypt. It is more time ago, started since 1952, and also in the present. This is, we hope that our relation make future for our countries. And this is people work in science, looking to improve our society as much as we can. People are working in material science. We must have one statement. It has come from Professor Tadahiro from Japan, that who dominates the material, who dominates the technology. This is the most important sentence that we must take in our account when we are working in material science. People producing material, it is, you have your own electronic industrial. All countries and the nation are producing material every day to making the society more happy and more comfortable for all the nations. Our talk will be consider some topic about our groups, some photos for our friends everywhere, and also senses of nanomaterial, nanocomposite, and application, electronic and optoelectronic devices, and the last one is the environmental application. Here it's our Faculty of Education, and here also our campus in Ain Shams University, our campus in King Khalid University. I am joined King Khalid University since 8 years ago, and we try to increasing our ranking of the university. We are working hard to deliver our university, both Ain Shams University and King Khalid, to be ranked all over the university. Here, our group in semiconductor, more than 23 years. I am joining this group. I am happy to join with my professor and my friends in the same laboratory, and also my students. In LEBA teamwork, this is our laboratory, are designed 3 years ago, and here our teamwork, it's come from all over Egypt, and we try to join all our friends to design material and characterization and application as much as we can. And here our ceremony for opening our laboratory with our student and colleagues. And here is our friend in King Khalid University. We have 3 friends from India. We have Dr. Ganesh, we have Dr. Shakir, and also Dr. Aslam. Really, I am happy to join all our friends here, and really we are work hard to reach what we needed to achieve for our department here and also our university. Here also we have a new group is about radiation shielding material that we try to design new material for shielding, and we try to join a lot of friends in Egypt and in Saudi Arabia and abroad to design shielding material using our material science. And here also our organic semiconductor group from Tabuk University joining us many publication now to design the optoelectronic material, photovoltaic devices, and the solar cell or organic solar cell in particular. Thanks for our colleagues and our joining friends from Egypt and also from abroad, from Russia, from Poland, from Serbia, really, and also from King Abdulaziz University here in Saudi Arabia. Really, we are trying to make a team. You cannot work now alone. This is before maybe 13 years, you can think that you can make everything alone, but now you cannot continue. So you must have friends, colleagues, and collaboration all over the world to produce your own science, and also to have a good collaboration and learning from all friends abroad. Here, this is the progress of publication during last 14 years. Really, we try to enhance our publication as much as we can. This is the most important scheme. Really, we are, since I am here, PhD student, you have nothing. You are just a student like everyone in the world. So, but you have a dream to make your own publication and to make your future. Future must be done by yourself first and then join the friend. The last increasing of our publication rate in last 3 years or 4 years, this has come due to the funding in King Khalid University to support the research and also to build our laboratories and to increase our facilities to produce science as much as we can. So the increasing of the publication here from 2017 until now, this is 4 years, we try to increasing the rate of publication as much as we can. Our publication also are limited. We try to concentrate it from 3 impact factor to 5 impact factor journal, and this is not easy to sustain yourself to publish such a huge number in the ISI journal, but we try to make our effort and the collaboration to increase our rate of publication as much as we can. What we have in our laboratory, this is available in AFMOL laboratory and in the LABA in Shams University. This is that we are looking for, and really we don't have much technology to produce material, but you have a low-cost techniques, and this is also very good and very interesting because you are not at Institute of Technology, but even you can have many techniques to produce material in both powder and thin film and nanocomposite. Design of nanomaterial depends about your mind and what you are designing for. So you can have your home-made design facilities, or you can buy from different company abroad. But we also try to arrange our facilities inside the laboratory and also inside our countries as much as we can. Different techniques are available really for cost-effective technique in nano scale, but we don't say that we are making sample in concept is called mass production of nanomaterial, and in both thin film and nano powder shape. For nano powder, we tried many techniques. It is cost-effective technique. We don't have much more technology, but you have your mind to design your experiment. And this is also for nano powder, you have microwave, hydrothermal, solid gel, co-precipitation, biosynthesis, and hydrothermal, electrochemical deposition, combustion, and bio-green synthesis. And for thin film technology, you have spin coater, chemical buzzed, electrochemical deposition, and deep coating, casting, and distribution casting for the polymers. This is enough to make your research and to learn more. You need years and years to produce material. By this is more than 11 or 12 techniques available in our laboratory. What we are really doing in our laboratory, we design different scale of material. We cannot sustain our material to produce only thin film or metal oxide or polymer. We are working with wide scale of material. What we have really more expert people here and to producing such a material, and this is material is graphene and graphene oxide composite, hydroxyapatite for bone cement engineering, lead iodide for perovskite, transparent conductive oxide, carbon dot, metal alloy, and finally we try to apply all of our material in powder and thin film for wastewater treatment. Before we are starting, this is the introduction for our friends group and what we are really doing in Ain Shams and King Khalid University for last 23 years in Ain Shams University and 8 years here from the same time in King Khalid. We try to design our material in nanoscale since 10 years ago. We are started nanoscale by solid gel thin films, and now we try to have some more ideas about nano design. But because we have also our friend here and student, we will start some introduction part about nanoscale and the senses of nano materials, and also nanocomposite, and we will show some progress from our laboratory and our friend about nanocomposite device, and also some polymeric membrane for environmental wastewater treatment. Nanoscale material, if you are scaling about nanoscale, so if you are talking about carbon nanotube of 1 nanometer diameter and multiplied by 100,000, you will have one hair here. And then if we are multiplied by 1,000, you will have 10 meter square, 10 meter wide house. This is the nanotechnology that people are looking for. This is nanomaterial or nanoscale material give a special characteristic of the material for optical, for magnetic, electrical device material, medicine applications that people now are interested to produce. Many of material now, if you are going down, so you have a motor, and then you have microelectronic shipping and design, but also you must start from the nanotechnology as self-organized material. And important here to show to our friend that if we are working with nanoscale material are the material within diameter or within the radius. Both are available, even it is diameter and radius, the same for us. For nanoscale, it is from 1 to 100 nanometer. And if we are, this is God invention for us, things in nature that it is in nanoscale. Like if you have DNA, RNA, this is all are in nanoscale material. But also people now, this is give also the same design of nanomaterial. You know, this is a gift from God, and also this is also since nano made also a gift, another gift from God to allow the people invention the same material to help the society and to overcome more diseases, and people need more technology now to be available for helping our society and the nations. Material can be classified in different categories. So we have zero-dimension material like nanoparticle, but also we have 1D 1D also nano fiber or wire or rods, and we have 2D material films, and also finally we have a 3D nano material. People try to engineering the nano material in everywhere, you know, to have design, and the concept here is called engineering, because engineering material is the most important scale that people are looking for here, to design the own material and to have your own characterization for such a material, and then lastly, and you can find the application. For material, people are try to design. This is more material, and now there is no border between different scale of material. Now people try to more years ago, they try to make some solid state energy biotechnology, but since 1990, people started to going more and more fast for nanomaterial and nanocomposite, and also for medical and microelectronic application. Now we are in this region until more years come the application of nanomaterial. Now it is very interesting for people are to join together to produce nanomaterial and nanocomposite for the future. More than 30 years, people are looking for nanomaterial and different application of nanomaterial. Nanomaterial, it is wide scale material now. People to try to design and engineering the nanoparticle to have tubes, plates, needles, spheres, and also to have different kind of material like metal oxide, metal composite, and also polymer carbon material, graphene and graphene oxide, semiconductor, and different compound together to form nano particle with different design material. Application of nanomaterial, the nanomaterial now it can be found in construction, medicine, engineering, chemical, industrial, and automotive industrial. But people are working in physics are more interested in electronic industrial, like to make laser diode, glass fiber, optical switch, filter, cut-off filter, conductive material. And also people are interested to make a lot of application, but people also in physics, chemistry are interested to make batteries, capacitor, and solar cell and fuel cells, but another cosmetic, textile, food, and sport also. Now all our society are working with nanotechnology and nano application. Before I said that we have different class of material and different class of material here, that we have a radius and we have a diameter. So if you have a nanoparticle, we talk about radius, and if you are talk about nanowire and nanotube, we can talk about diameter. But we must say, if you are produce your own material and your material it is larger than 100 nanometer, are you work with the nanoscale or not? Yes, sure, you are working with nanomaterial. And but the material after 100 nanometers, the material started to be accumulated and forming something is called nanocluster. And you are in the same region, but better to design your own material to be within 100 nanometer. If your material radius is less than 10 nanometer, you are working with quantum dot, and the people try now to design the new material in lower size to be in quantum dot application within 10 nanometer. Different kind of material with different kind of application and different kind of properties can be elaborated for the future of material science all over the world. People try to reducing the size and to reach it more device with special characteristic for these devices, and try to reduce the price of the device as much as we can. And this has come because we are interested in material science. People are happy to design material with nanostructure, especially semiconductor in both chalcogenide or film is organic, inorganic, and a lot of material can be used widely now, not only to be for just producing a material, but now the device application are the most required now to have a device. So people are interested to make diode, Schottky diode, nanocomposite diode, and also transistor, field effect transistor, also magnetic material, that people are looking for the future of material science and the engineering of the material. Important, we will go to started now experimentally what we are really doing in our laboratory with cost-effective techniques to produce nanoscale material. You have two approaches you must take in your account if you are working with material science or nanomaterial science. The first of all, you must have top-down or bottom-up nanomaterial design. So if you have a bulk sample, and the bulk sample, you needed to reduce the size to have a small cube, and then a small cube can form a nanoparticle or nano rods or wires. And this is also called from the big scale material to have this big scale material to be reduced as much as we can to be in the nano scales. But in the same time, we have a bottom-up nanoscale material designed by, you have a useful atomic material, and by atomic material you can design this material to form a cluster, and then cluster forming a good shape with nanoparticle or nanotube or nanorods, as illustrating in this picture. We have different methods for creating nanostructure. In our webinar, we will concentrate about 4 categories of preparing nanostructure material, and this is can design in your laboratory easily, and you have in your lab, and then you can very good to produce nanoscale material in easiest way in your lab. So the first one, we will speak about mechanical ball milling or mechanical grinding of this material. This is popular method to produce nanoscale material as a top-down. So we have a more bulky material, and this bulky material, we needed to reduce its size. So we have stainless steel autoclaves, and this is stainless steel autoclaves have the powder inside in stainless or in Teflon or in other cubed, but stainless is the best way. And you have a balls from titanium or zirconium or stainless also to reduce the size of the powder. And by ball milling in a special device here under different frequency of the system, you can design your own powder, and you can make your own material in special color and also in very fine powder and in nanoscale. This is also need some time, and some expert people are working in designing this material by ball milling. This is also available techniques and also available in the market to reducing the size of the material. But in the case of ball milling, we have special, if you have two different class of material like titanium nano powder or titanium powder with multi-war carbon nanotube, and you needed to grind it together to have titanium doped multi-war carbon nanotube. The best way for you here is ball milling or mechanical grinding to have titanium composite with the carbon nanotube, and this is you have a good structure of this material by this grinding, because if you are apply furnace here, the titanium melting, it is over 2000 Celsius, and it is not easy to have a furnace 2000 in your laboratory. So the best way for you, if you need to combine some material, the ball milling is highly approached for design such material. But you must take care here. We are trying to work or to provide some experience about producing the material in your own laboratory. You must take care about the impurities of your material here, because the interaction of stainless steel, stainless balls with the stainless here can produce some very fine powder come from the stainless itself, and then it will be some impurities inside your stainless steel autoclave here. So you must check and make some elemental analysis if your the required material contain impurity from the balls or from the autoclave itself. This is one disadvantage of this material. Second of all, if you are designing the material in your laboratory, the best method that available and can be produced in your own laboratory is with chemical method using sol gel process. First of all, this is second stage that we are interesting, and this is can done in any chemical or physical laboratory. Now it is very easy to produce nanoscale material from with chemical or from solution. So we have a sol gel. So sol gel meaning that you have two termination here. So the first one is sol, the second one is gel. So if you have a precursor, precursor for us here, we have different precursor in the laboratory, and we will talk about some advantage and disadvantage of these precursors. And for this precursor, if you are design the material, that we must talk about nitrate, acetate, and chloride, sulfate, carbonate. But the best material for nanoscale material is nitrate, because nitrates under temperature 450, nitrate will leave your metal ion, and it will be no impurities come from the precursor itself. Soluble in different material, and then you can have a sol. If making some dehydration and lifting in dark place, then you will have a gelling. By rapid gelling, you can reach it in the final stage, even in powder and in thin film coating, the dense film or nanoscale powder under calcination. Here, we must talk about important things that we need to require of this material. what is the optimum temperature for producing thin film coating if you are working in glass? So the maximum temperature will be 450. You can increase until 470, but don't go more because the glass substrate will be destroyed. So better for our sample in sol gel thin film technology, metal oxide, it is best, the best for this temperature, it will be 450 Celsius. But for nano powder is most important for us to be dispersed in polymer or making a membrane, and also for photocatalytic material or to make a material for evaporation with vacuum or electron beam, laser beam. And this is the optimum temperature here is 550 Celsius to ensure that your material don't have any nitrate ion inside your matrix. So we have two categories of temperature here. The first one for thin film technology, maximum 450, and for nano powder, your temperature, the optimum temperature to start 550. This is you can have a pure phase of metal oxide, but people can also try to drying material in 100, 200, 300 until 1000. But if you have only one temperature and you needed to require your temperature to produce nano powder in single phase, and important to say that it is single phase, because in some design of nano material you have multi phases inside the production of material. So for powder 550 is the Celsius is the optimum required for obtaining single phase from different materials. So this is for our progress. So sol gel, aged, dried, and you can have also porous gel and then dense gel. This is different stage of your material here. You can design this material also with temperature and also sustain some principles here until 120, and the final stage will be 450. This is for sol gel precursor, but we must here, if we are talk about sol gel, important to say something is for our colleague and our student. If you have acetate precursors, so you will have carbon inside your material. If you have a chloride, the chlorine cannot be evaporated easily from your material. You must, if you have cadmium chloride with hydrated cadmium chloride and you needed to make cadmium oxide, you must raising your temperature until 800 Celsius to remove the chlorine. It is not easy to remove chlorine from your material, because in the first I said better if you produce nano material to have a nitrate source. This is will be important for you to have a single phase material. Third and most important, people now are working, and all the laboratory all over the world concern furnace, and how people now producing material with furnace as a biosynthesis or green synthesis of nano material. So if you have a furnace, you have a crucible, and this crucible ceramic or alumina and other crucibles can be also be inside the laboratory, and then you have your nitrate material with a small molecule foil material. This is foil material, can be different stage here as starch, gelatin, citric, and glucose, and the gum acacia. Really, we are designing beautiful nano material using starch, gelatin, citric, glucose, gum acacia, urea, cyurea, all are available in our laboratory. And by mixing with nitrate, you can design your nano material with different concentration from starch, gelatin, citric here. And the best concentration, if you have a 5 gram of zinc nitrate doped with starch, gelatin, citric, the optimum here to have a good nanostructure to apply 1 gram from each of this material to have a good nanoscale material. And you can have different kind of material by changing the concentration of the foil material. The foil material here is highly appreciated to design the nano material like zinc oxide, cadmium oxide, magnesium oxide, and others. But in some cases, you will have some carbon inside, especially when you are working with the citric acid. The citric acid here is give some carbon inside the material. So sometimes you are working with carbon doped zinc oxide. Better to have citric acid. Don't use starch or other material. Third techniques that available in our laboratory. You can design your own. This is actual picture of our homemade microwave senses of silver nanoparticle. In 5 minutes, you can have a silver nanoparticle using domestic microwave, and this is domestic microwave operated in the frequency 2.54 gigahertz, and you can design also metal oxide powder and the thin film metal chalcogenide, and also metal ions like or metal nanostructure or nanostructure metal by using your own homemade design microwave. Different techniques are available in the market and also in your laboratory. You can design with the same scheme, the same produced in the laboratory. This is our actual picture, and this is the same. It is available in the market, and this is also highly expensive. But here with very costly, you can arrange your own here to design your material. Just you needed to make one open here in the microwave and connect your condenser and flask here with water flow, and then you will have a very beautiful silver nanoparticle with 5 nanometer here. It is very easily to produce in microwave and domestic microwave. This is microwave techniques are very important, have more advantage in using in nanoscale material, especially if you needed to prepare nano silver or nano gold or nano platinum or mixed metal together. So because it is have less waste and less energy consuming, avoiding accidents, and also you can control your parameter for designing this material. And you have here in this system, you can control the time and also the power of the system, but you cannot control the pressure. But in other systems, in highly expensive microwave, you have a 3 important parameter: temperature and pressure and temperature and pressure inside the system. So you can have some more designing of good material for your application. Fourth techniques is available also in our laboratory is the hydrothermal synthesis. This is all our techniques are cost-effective techniques, and hydrothermal synthesis is highly appreciated to design material and to have a good material with a good surface area, and you can also control the structure of the material. So this is hydrothermal autoclave, and you can sustain your temperature of the autoclave. If you have a Teflon inside, the maximum temperature will be 200 Celsius inside the Teflon. And for if you have stainless steel without Teflon, you can sustain your autoclave until 800 Celsius with safety. But you must take care that hydrothermal also, it is very dangerous if you are working, because you have a pressure come from the water. It is called the hydrothermal because you have a water inside. If you have another solvent like ethanol, methanol, and acetone, so you have solvothermal synthesis. But you must take care because this is a bomb. This is explosive. So you must, if you have working with the hydrothermal autoclave, better you have a special room with a special control from outside the room to control your material, because explosive can be happened in designing of this material, especially when we are going to very high temperature. You must make you and your friend in secure place. We will go faster for functional smart and functional nanomaterial. This is our ordination, you know, Pharaohs, Indian, Chinese, are Romans are producing beautiful cups with good color, sustained for thousands of years until now without change. How they are knowing all of this information? They are designing a material like us, but 3,000 years ago. people are intelligent and they don't have much technology, but they have the mind to produce such beautiful cups with beautiful color, and the color sustain for 3,000 years, 4,000 years without any change. This is the intelligence of our nation and ancient nations before. And also some people are designing and painting inside the glass with nanoscale material also, but and this is, as you see, the beautiful color not changed until now, because they are expert to having lasting the material for more years and to design beautiful windows as it is shown in this screen. If you are working with the nanocomposite, so you have two termination here. You have a nano and you have a composite. So if you have a nanos, you are working with 1 to 100 nanometer, and the composite is the matrix that we are needing. So you can have different class of material. This is different class of material here can designed inside the matrix, as you see from multiple phases material. Multiple phases material is highly appreciated to have a multi-phase material in one place. So different scale of material that can be designed in nanocomposite. So if you have a matrix, this is matrix is called polymer-like. So you have a polyvinyl alcohol PVA or polymethyl mesacrylate PMMA with a filler. The filler here will be different kind of material, like 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional material. You can add it to the matrix. This is matrix will be the host, and the filler will be the doping for your matrix. What is the benefit of this is nanocomposite? Nanocomposite now, this is most required now for the people are working in material science to produce very good and to have a good characteristic of such nanocomposite for airplane, for cars, for ships, for designing construction. All are also for solar cell material and for membrane and for device engineering. Now people looking to good feature of the material. How to obtain good feature of the material? Material itself cannot be enough for designing good material. People try to design different material together to have a special and a special feature of the device and for different applications. Here, as I mentioned before, here we have a filler or a filler, and we have a matrix, and then you have a composite or nanocomposite material, and then here the nanoparticle are inside the random matrix of polymer. Here's the same thing is that you have also nano-shaped microcomposite or nanocomposite material with the filler, and you can design very beautiful material and with different shape insides. We will go fast that we have one good example here about polyaniline doped with cadmium sulfide. So we try to, if you have a polyaniline, you try to make cadmium sulfide in situ to join this material, and to have a cadmium sulfide, you have different steps to producing cadmium ion and then sulfur, or using H2S, and then you can have intercalating with the nitrogen inside the matrix of polyaniline. For the requirement of nanocomposite, important the mechanical properties will be in enhancement, and also optical properties of material will be showing some enhancement, and this is that we needed to enhance the conductivity, the optical properties, the resistance, reduce the resistance of material, and to increase also the mechanical property of such material. How you can characterizing your own material? Nanocomposite can be designed by different categories. Important here, this available in our laboratory: X-ray, atomic force, scanning electron microscope, transmission electron microscope are most available in university or inside the country. So you can also design your material and make some characterization of this material by using scanning electron microscope, and you can design find the elemental analysis by using EDX, and also the same can be done by high resolution TIM or TIM. You will also find good structure, and you can find your host matrix and also the filler inside by using high resolution TIM. What two important things that I needed to deliver to our friend and our student? If you are working in nanoscale or nanocomposite, there is some secret in behind. People are doing material inside the laboratory. Important to have this has come from the experience, and this is need more and more years to design material in your laboratory. So two important things you must taken in your account if you are producing nanomaterial and then nanocomposite taken in your account, and we will see what we are looking for. The first one, if you have zinc nitrate and you need it to overheat it in the furnace at 550 Celsius, are you will have a nanoscale material? Sure not. This is cannot be producing by if you are burning salt of metal salt inside the crucible in the furnace. But you allow some techniques with some helping of the material. So if you have a green synthesis of the material, you will have here some fuel material that I mentioned before, like starch, glucose, urea, cyurea, gum acacia as a fuel to destroy or exfoliated the crystal structure of zinc oxide. So you can have the nanoscale if you are just make combustion technique of your metal oxide or metal salt to have a metal oxide. But if you are working with the chemical like salt gel, so you will have if you are soluble material in water and then drying, gelling, and then calcination, are you willing to will have a nanoscale material by using salt gel? Approximately, maybe not. If you found in one material, you cannot find with the others. The most important category you must take in your account when you are producing nanomaterial, you having surfactant. If you having surfactant inside your solution, like cadmium nitrate with surfactant, so you will, inshallah, having your material in nanoscale. Without surfactant, you cannot control the wet chemical synthesis of nano structure. Nano structure important that we are like to produce our material, you must have CTAB. Different categories of material can be using as a surfactant. We have anionic, cationic, and non-ionic, and different. But the most popular for the people are working in nanoscale to have a CTAB. This is cetyl trimethyl ammonium bromide, and the short name is CTAB, and also sodium dodecyl lauryl sulfate, SDS. This is the chain of the CTAB and the SDS. You must take in your account the best material for nanoscale design is CTAB, because CTAB it is easy to clean and easy to remove from your material after washing. But SDS, as you see, it contains sulfur, and the sulfur may be contaminated your nanoscale sample, and this nanoscale sample can be have a sulfur inside. So you will have zinc oxide, but the sulfur maybe it will be as a doping inside. So the color of the material cannot be a white, but in the same time, the nanomaterial will be like ball yellow or yellow a little bit, because the sulfur inside the zinc oxide. This is meaning that you are not cleaning the sample in the best way. For our experience and people working in our laboratories, we are using CTAB, and the CTAB is the best material for producing nanoscale material without impurities inside. Different class of material can be also used as a surfactant: oleic, PVA, PEG, twin, span, triton, and other material can searching about anionic, cationic, and non-ionic material can be used for designing this material. This is one important thing for our student when designing the material to using CTAB in your with chemical synthesis, especially by Solgel. Another important secret in behind when you are working with nanocomposite or nanocomposite material, you must have a sonication in your laboratory. Sonication is the most important techniques when you apply as we say, this is nanocomposite, and you will have a BVA or BMMA matrix, and you can add some filler inside. But you added the powder and using a magnetic steeler to have dispersed of the powder, but maybe this is not enough to using a magnetic steeler. You must have a homogenizer or ultrasonic system, sonication system, to exfoliate the dispersed powder inside the matrix, so you can have a homogeneous matrix after using sonication. So two important things that I needed to deliver to our student. First one, to using CTAB. It is most important to produce nanomaterial, any kind of nanomaterial, ceramic material, semiconductor material, chalcogenide material, metal oxide material. This is most important to using CTAB. The optimum concentration for CTAB, you must take in your account 10 gram per liter or 15 gram per liter. But if you needed to have different structure, you can change the concentration of your material. And for our experience here, is the best material for us is 15 gram per liter or 20 gram per liter. We will go fast because our time is limited, so we will go some application of this devices. So you have some electronic devices and some cut-off laser filter using different kind of material like titanium and polyvinyl nanocomposite for laser attenuation, and also you can decrease the power intensity for laser ablation, for laser operation. Now in medical, you needed to design and to decrease the power of the laser. So better for you to using some filter using from polymer and other techniques. Also, some of our friends making semi-transparent Schottky diode using polymer misaccelerate with multi-war carbon nanotube as application of nanocomposite material with as a carbon-based nanocomposite, and they have photovoltaic behavior and photoconductive layers. Also, my friend also producing non-volatile memory based on some carbon structure, multi-war carbon nanotube with organic on the silicon as a hybrid heterostructure, and you have very good and beautiful memory diodes. Also, we are interested to producing and decreasing the power of the laser. So we make here not a stand-free sheet of polymer, but we can make a thin film layer of dirhodamine B doped with polymethyl misaccelerate over a conductive glass for laser power attenuation. And this is our approach here to decreasing the power of the laser. Two lasers here are applicable as helium neon laser with low power and the green laser with approximately 20 milliwatt. And then it is easy to decrease this power of the laser, as it is mentioned here, by using a very thin film layer of rhodamine B doped polymethyl misaccelerate over a conductive glass. Another group in abroad, they are designing Schottky diode or metal semiconductor diode with semiconductor behaviors, and they try to design many kind of material like zinc doped polyvinyl alcohol as a diode. And if you are interested, it will be very good and very beautiful if you have a BVA doped with cadmium sulfide, BVA doped with zinc, and BVA doped with nickel acetate. All are in the same category of polymeric. This is the new trend inside the world now, not to only using one junction like before, cadmium sulfide over silicon, and then they can make a diode. No, now people are using low-cost technology of using polyvinyl alcohol or polymethyl misaccelerate with different kind of material to producing polymeric diode or nanocomposite polymeric diodes. Now we will go to a second application to using in our laboratory. We're producing graphene doped polymethyl misaccelerated stand-up sheet for nanocomposite membrane for environmental photocatalytic, and this is some good picture for scanning electron microscope, band gap analysis, and dielectric properties of your sheet. And then finally, we try to make catalytic activity or photocatalytic activity to have composite by using this composite to photo degradation of amoxicillin, and it will be very good and very beautiful to have catalytic material as a membrane, so it is easy to clean your solution and it removes the membrane. But if you are concentrated here, we will have a second, and this is our accepted paper 10 days ago. That is also, we have a flexible photocatalytic application using cadmium sulfide and polymethyl misaccelerate, and this is designed in our laboratory to also photocatalytic degradation of some dyes like rhodamine B, and we are successfully to having polymethyl misaccelerate. But one say, why you don't using here polyvinyl alcohol? Polyvinyl alcohol will be swelling inside the water and you cannot have a good film. But polymethyl misaccelerate, it is not soluble in water and better to be used as a membrane as a photocatalytic application. Last important material that we are producing in our laboratory is a lead iodide. Lead iodide now is a very beautiful material, even it is contain lead, and lead it is toxic. But lead iodide, it is now going more fast for producing perovskite solar cell, and be able to reach it 22% easily, and try to stable this perovskite by different structure of doping this lead iodide by different category, even with mercury. So you have a very good material, and you can design also this material because it is lead iodide and mercury. You can also have some radiation shielding parameter for this lead iodide as it is work in our laboratory. So this is from the screening of such things. It is important for all of us to mention that nanocomposite devices is highly required, not only to laser power attenuation, but it is also in photodiode, in memory diode, in field effective transistor, and also for photocatalytic activity as a nanocomposite polymethyl misaccelerate with cadmium sulfide, with graphene, with other doping as much as you can. You can doping material as you can think. It is better. And finally, I must think that you can not work alone in this time, especially in 2020. This is important to have a collaboration with the people abroad and inside your nation to increase your work quality, and best to important say that you must be together. This is the most important word, that you cannot make your own science now alone. Thank you very much, and really I am happy to join with this webinar with our friend, and thank you, and thank for the organizer.
Thank you, sir.
Our screen on the
Thank you.
Hello. Sir,
Thank you very
sir.
much, sir, for your nice presentation. All the participants enjoyed your presentation and posted positive comments on the chat box.
Thank you.
They asked some clarifications. Whether using nanocomposites for sir, whether using nanocomposites for environmental applications or cost effective?
Again, brother?
Whether using nanocomposites for environmental applications or cost effective.
This is, if you are applying, two last mentioned papers here, polymethyl mesacrylate with graphene and also polymethyl mesacrylate with cadmium sulfide. We try to make a membrane with polymeric matrix, and we have a good result about photocatalytic degradation of antibiotic as amoxicillin, and also for some dye waste inside the water. So it is give good efficiency, better than using polymethyl mesacrylate and also to using cadmium sulfide alone. If you have a nanomaterial inside the matrix, so it is easy to clean the matrix and remove this matrix from the water, and the cycles of this material cannot be destroyed as a membrane inside the water. But if you're using a membrane, better to have a material that it cannot be soluble inside the water. So I recommend it in our work to using polymethyl mesacrylate as a host matrix, and you can doping with any filler for wastewater treatment and to degrade antibiotic, phenol, and dye also.
Next question. What are the factors affecting the functioning of nanocomposites towards the environmental applications? Especially tell the practical difficulties that you faced in your laboratory while handling the nanocomposites.
Yeah, this is before we have sonication. So if you have just only using a magnetic stealer in your laboratory, maybe you cannot have a uniform and homogeneous membrane, especially if you are working with polymeric nanocomposite. Magnetic stealer may be not enough to have a homogeneous and highly dispersed nanoparticle inside the matrix. But when we are reaching to have apply ultrasonic process or a homogenizer for this polymeric membrane before the casting solution in petri dishes or stainless steel dishes, so better to make ultrasonication minimum power with 120 watt for minimum 5 minutes. You apply for your own material to have a highly dispersed nano powder inside the matrix, and then after that you can make a casting. The most difficult is to have a homogeneous membrane or a homogeneous dispersed nanoparticle inside the matrix, and we try to overcome this by using magnetic stealer and also by sonication process.
Professor, to improve the conductivity of nanocomposite material, what are the steps we have to do?
Increasing the conductivity here, you must, if you are working with the polymethyl mesacrylate, it is dielectric material. It is highly dielectric material with band gap reached 5 eV. So if you are doping this material with cadmium sulfide, zinc oxide, the filler, if the filler has a low conductivity, then the final matrix of polymethyl mesacrylate, the conductivity of the matrix and the resistance of the matrix will be decreased according to the filler. This is also highly appreciated to have a conductive nanomaterial, and to prepare conductive nanomaterial, both important to have some special doping like indium, like gallium, like aluminum, like fluorine, and then you can have less conductivity or decrease in the conductivity of nanopowder. And if it will be inserted in dielectric media, the conductivity of the total matrix will be decreased.
Thank you, Professor. You have explained very well about the nanocomposites, and in so many applications you have explained. One of your applications, second applications, in one of your slide, it tells that the transmittance increases and gets a maximum value and then slowly decreases and gets a very minimum value. So at this minimum value, what happens to the transmission spectrum? Whether things are observed or reflected? Can you give the significance of the minimum value of the intensity?
I think here, sir, this is that you are looking for, yes?
I think it's the second application.
Yeah.
No, one more slide, I think. It's also that happens like this. One more slide, I think. Okay, Professor, you can give the significance of the minimum in intensity value. Sorry, transmissions.
Yes, I can hear. This is our trend in work. More than 5 years ago. So we are producing. And also, you have a conductive glass. This is the conductive glass, fluorine doped tin oxide, and for fluorine doped tin oxide, here this is the shape of the design of this material is have a special character than other substrates they are using. So if you have Fe2O, this is the characterization of the Fe2O. This is you have Fe2O is the fluorine doped tin oxide, and this is easily produced in the laboratory if you have a fluorine with tin oxide spray pyrolysis. So you can have a very ohmic material, 7 ohm or 15 ohm or 20 ohm layer of fluorine doped tin oxide over glass. But what we are really here doing, we have here, the Fe2O properties as a pure Fe2O. But if you have a rhodamine B doped with polymethyl mesacrylate as a doping of dye, this is fluorescence dye with the polymethyl mesacrylate. So you can creating beautiful absorption bands here inside the Fe2O. So if you are designing this material, the Fe2O matrix will be dominant in your material, but you are creating new absorption band inside this material. And for this material, you will have different categories. So you will have the first band gap for Fe2O and the second band gap for your rhodamine doped polymethyl mesacrylate. And for this is low, the low transmittance here. This is come from the feature of the substrate itself. The substrate has its maximum around 82% in the visible region, and they are blocking the infrared light region here. And this is highly recommended now for the device engineering and for using this material for wide scale, that people deposited different kind of material, not using glass now, but they are using conductive glass, because this is conductive glass removing the IR signal from the light, and then the light cannot be heated when working with optoelectronic devices, because the IR region or IR light will be absorbed due to the Fe2O layer. So the decreasing of the transmittance, it is not come from the material, it is come from the substrate, and the substrate control the behavior of the device.
Thank you, Professor. Thank you.
Sir, one last question. Can you give some nanocomposites which are used for water treatments?
Yes. So for water treatment, some important material people are using now different class of nanomaterial to be in the composite. People are, if you are working with the degradation of the light with UV, so you will have around the lamps will be 367 nanometer, better to work with zinc oxide and the titanium oxide inside the membrane. But if you are working with visible light lamp for degradation of your waste material or for environmental application, better to have cadmium sulfide. Also, you can have silver phosphate. Ag3BO4 is also highly recommended. But also, people using now another very good category of material like bismuth vanadate are also highly appreciated now to be more suitable. But even you are working with cadmium sulfide according to the material available in your laboratory. So better to doping cadmium sulfide with different class of metal ions, and then you can control the band gap, and then you can have a beautiful photocatalytic application and environmental cleaning using polymethyl mesacrylate. I recommended polymethyl mesacrylate to be using as a membrane because polyvinyl alcohol cannot be suitable for this application. And this is the most important two class of material. If you work with UV material, you can work with silicon oxide, zinc oxide, titanium oxide. And if you are work with the visible photocatalytic application, better to work with cadmium sulfide, silver phosphate, and bismuth vanadate. This is the most important material people are doing, and you can make different doping, and then you can have different class of material and reach the high quality and the efficient membrane for environmental applications.
Thank you, sir. Now I invite Dr. A. Sanmugaraju, Dean Academic Affairs, to deliver vote of thanks.
I'm very happy to propose formal vote of thanks in this international webinar conducted by our department on the progress in nanocomposites for environmental and device applications. First and foremost, I would like to thank on behalf of the organizing committee the management of our college, especially for the rector, Reverend Father John Pragasam, who has offered felicitations, and Father Secretary, Reverend Father V. Gilbert Camillus. Both of them have offered felicitations with some ideas on nanoscience and nanotechnology. Thank you, fathers. Next, I would like to thank our principal, Reverend Father U. Godwin Rufus, for motivating all the participants with his presidential address. Next, I thank our head of the department, Dr. K.S. Joseph Wilson, sir, for organizing such a wonderful international webinar on nanocomposites. Special thanks to Dr. Wanga Ganesh from Andhra, who is working with the Professor Yahya. We wholeheartedly thank the resource person, Professor Dr. I.S. Yahya, Semiconductor Laboratory, Egypt, and Associate Professor in the Faculty of Science in King Khalid University, Saudi Arabia. Thank you, Professor, for spending your valuable time for all the participants in explaining nanocomposites with the environmental and device applications. You have elaborately explained the classification, importance, design and synthesis, and applications of nanomaterials by quoting your own research papers. Thank you very much, sir.
Thank you, sir.
Next, I would like to thank our colleague, Dr. Valanarasu, for arranging the resource persons and organizing such a international webinar. Thank you, Valan. Next, I thank all my colleagues in the Department of Physics, especially Dr. C.S. Raj, Dr. Anthony, Dr. Jacob, Dr. Thomas, Dr. Rex Rosario, and all others who have spent their valuable time and arranged this international webinar on nanocomposites. Lastly, I thank all the participants of this international webinar from India and abroad who have actively participated and got benefited from this webinar. Thank you. Thank you all. Have a nice day.
Thank you very much.
Thank you. Thank you, Professor Yagiya. I am Dr. C.S. Raj.
Thank you.
Participants.
The link has been sent to the chat box. The participants, please register your feedback form. Thank you. Now you can
Okay, thank you.
Thank you.
from the
Thank you, sir.
webinar.
Thank you, sir. Thank you so much for your wonderful